In this video here, we're going to take a look at volumes of revolution about the x-axis. Now, hopefully the concept here of volumes of revolution is not new to you, and that doesn't matter whether it's about the x-axis, as we can see for this video, or the y-axis. And the reason for that is because we've already seen an introduction to volumes of revolution as part of the first year material here for Core Pure. That was Core Pure 1 material. Now, for this video here, then, what we want to do is basically just extend volumes of revolution to account for trickier functions that could now require any integration techniques that we have learned in A-level maths. So for example then, we have integration by parts, integration by substitution, trigonometric functions and trigonometric identities, and then finally here, exponentials and logarithms. Now, this list here isn't exhaustive, but do ensure you are confident with all integration techniques from A-level maths. Obviously, integration is fundamental here to volumes of revolution, so a good basis and understanding then of the integration skills and techniques from A-level maths will make this chapter here on volumes of revolution a whole lot easier. And then finally here, a quick formula recap. So, the volume of revolution formed when y equals f of x is rotated 2 pi radians about the x-axis between x equals a and x equals b is given by the following result here. So as we can see then, v, the volume here, is equal to pi times the integral from a to b of y squared with respect to x here, so dx, right? And again, hopefully you are familiar with this result here. We've already introduced this as part of the first year material then for Core Pure. So there we have it. It's a very quick introduction really to volumes of revolution about the x-axis, but we're not really introducing any new theory here or anything like that. We are just largely recapping the first year material here then for volumes of revolution. So let's get started here then with one example for volumes of revolution about the x-axis. So let's get started then on this example here for volumes of revolution about the x-axis. So what do we have for this question here? Well, as we can see then we have this diagram here, right? And this diagram then shows the curve with this given equation here. So we have y squared is equal to 4x plus 9 all over here 2x plus 1 times x plus 4. We're then told that the shaded region R is bounded by the lines x equals 2, so that's this dotted line here, x equals 5, so again, that's this dotted line here, the x-axis, and the curve. Okay. We're then told that the curve is rotated through 2 pi radians about the x-axis, and the question here then asks us to use calculus to show that the exact volume of the solid generated is pi ln 33 over 10. So where do we begin here then? Well, hopefully you might recognize this straight away. But what we need to use here then is partial fractions. And why is that the case? Well, for the volume here, v, that is equal to pi times the integral here then from a to b. So a in this case would be 2, b would be 5. So from 2 to 5 here. And because we're going about the x-axis here then, we integrate y squared with respect to x then. So y squared dx here. Okay. Now, we already have y squared here, right? I've got y squared is equal to this algebraic fraction here, but trying to integrate this algebraic fraction here in its current form isn't particularly great, right? So what I want to do then is take this algebraic fraction here and split that into partial fractions. So given that you're studying A-level further maths, hopefully partial fractions is pretty much straightforward, right? So I'm not going to go into too much detail here for the partial fraction decomposition. I'll quickly show you what I did then. So partial fractions here. So for partial fractions here then, what do we get? Well, I've got 4x plus 9 over then. So I've got 2x plus 1 times x plus 4. X plus 1 times x plus 4. And that here then is identical then to a over 2x plus 1 plus b over x plus 4 here. Okay. So what I get then is a lots of x plus 4, a lots of x plus 4, plus b lots of 2x plus 1. And that then is identical here to 4x plus 9. Okay. So for example here then, if we let x equal, say, minus 4 here, so let x equal minus 4, then this term here will disappear, right? Because minus 4 plus 4 is 0. A times 0 is 0. So then we can go on to solve for b here. So in that case, then what would I get? I'd get minus 7b here. So we get minus 7b is equal to minus 7. And therefore, in that case, then b is equal to 1. Okay, hopefully nice and straightforward there. Doing the same then to solve for a here. If I let x equal, say, minus a half, then let x equal minus a half here. What would we get here then? So I'd get 7 over 2b, 7 over 2a even, 7 over 2a there. And that is equal to 7. So in that case then, a here is equal to 7 divided by 7 over 2. And that would give us 2 there. Okay, so a here is equal to 2. So altogether then, what I've got here is 2 over 2x plus 1 plus 1 over x plus 4. And trying to integrate this here now is much more straightforward, right? So in that case, then we can now rewrite v here. So in that case, then v here, the volume is equal to pi times the integral here then from a to b. So again, from 2 to 5, the limits won't change, right? So from 2 to 5. And for y squared then, well, if I just rewrite it here, y squared then, rewriting this as its partial fraction decomposition here, we get 2 over 2x plus 1. So 2 over 2x plus 1 plus b over x plus 4. So that's 1 over x plus 4. Like so. So this is y squared here, right? So y squared then, we are integrating 2 over 2x plus 1. Like so. And we also have 1 over x plus 4 here. Okay. And we're integrating here then with respect to x, so dx. Okay. Now for each fraction here, we just notice then the derivative of my denominator is equal to the numerator here. So the derivative of 2x plus 1 is 2, which is the numerator. Same again here for this fraction then. So the results are nice and straightforward. What I get here then is pi times by. So this result here then, this would be ln of 2x plus 1. We get ln of 2x plus 1. Same again then here for this fraction, I'm going to get ln of x plus 4. So plus ln of x plus 4. Like so. And we go from 2 to 5 here. Okay. So now let's substitute in our limits here. So remember, we start with the upper limit, subtract the lower limit here. I've got pi times by here then. So I'm going to get ln. So 2 times 5, which is 10 plus 1. I get ln 11. So ln 11 plus, that's going to be ln 5 plus 4, which is 9. So ln 11 plus ln 9. We then subtract here the lower limit, so minus then. So I'm going to get ln of, well, that's 2 times 2, which is 4, plus 1, I get ln 5. Doing the same here then. So ln of 2 plus 4, so that's ln 6 here. So ln 5 plus ln 6 here. Okay. If we then simplify this here, what would I get? Well, I get pi times by here then. So ln 11 plus ln 9, that's ln 99. So ln 99 there. Ln 5 plus ln 6 is ln 30. I've got minus ln 30 there. What I could do now then is write this as a single logarithm here. I've got pi times by ln of 99 over 30. What we can do then is simplify 99 over 30 to give me 33 over 10 there. So that is equal then to pi times by ln of 33 over 10 as required. Okay, so as required there, and question complete. So there we have it, bosh, that gives us our solution there. And that brings us to the end then of this video here on volumes of revolution about the x-axis.